Yes, we can.
Yes, we can hear you.
I'm going to experiment with buttons for lighting here, but I don't know if you guys already.
It's okay.
Hey, okay.
All righty. You want more lights on?
I just turned some off, so I think if
Is that good? Okay.
I think that should be fine.
Okay.
All right. Well, thank you all for having me. It's been great. I've spent part of today visiting the university and spending some time here, and I'm excited to tell you all a little bit about the dark side of the universe and sort of work that I and colleagues do to try and use observations of the large-scale universe to learn about fundamental physics. So my research is in theoretical cosmology, but kind of focused on the area where theory meets data and trying to get, the universe to tell us how it works. So the sort of rough outline of the talk is I'll spend some time talking about a little bit of an intro to dark matter and dark energy, which are these big open questions in cosmology and just in physics in general. And then I'll kind of go from there into how we can use measurements mapping the distributions of galaxies in the universe, or galaxy surveys, of which the experiment I work on called the Dark Energy Survey is one, to try and learn about dark matter and dark energy. So I'm happy to take questions as we go. And at the end,
You can ask people to put questions in the chat.
okay, yeah, and if people put questions in the chat, I think people are monitoring. And
Thank
yep. Okay. So let's start talking about what I mean when I'm very dramatically saying the dark side of the universe. I am referring to this picture of the universe that we've constructed with many kinds of observations over several decades, describing the contents, the composition of the matter and energy in the universe. And what this pie chart shows is the present day fractions of matter and energy in the universe made up of different substances. And so you're going to also see, somewhat self-indulgently throughout this talk, I like to draw cartoons to try and explain some science concepts. You're going to see some of my illustrations of varying quality. So the really notable thing about this picture is that it's only the smallest piece of it, making up 5% of the matter and energy in the universe, that's made up of stuff that we really know how to describe on a fundamental level. So basically, this is anything made of atoms, protons, electrons. That 5% is all of the matter that makes up all of the stars and all of the galaxies and planets and lecture halls and podiums in the universe. That's all only 5% of the matter and energy in the universe. And the rest of it carries these mysterious sounding names, dark matter and dark energy. And we would like to know what they are. And the sort of general outline here, and then I'm going to go in a little bit into a little more detail on each of them. Roughly speaking, dark matter, which makes up about a quarter of the mass and energy in the universe, is a substance that we're pretty sure is made up of probably some type of particle, but we don't really know what it is, but a type of matter that interacts gravitationally in the same way that ordinary matter interacts through gravity. And we infer that it's there and its properties based on how it interacts with visible matter gravitationally. But as opposed to normal matter, which interacts through electromagnetism and other forces, dark matter, as far as we can tell, doesn't interact with any forces other than gravity, or if it interacts with other forces, it's very weak. So in practice, that means we call it dark matter because it's invisible. The biggest piece of the pie, which I guess I should probably use this pointer, is labeled dark energy. This is about 70% of the present day mass and energy in the universe. And dark energy is a name we give to whatever is causing the expansion of the universe to accelerate. So I'll say more about this yet, but sort of in contrast to dark matter, it doesn't seem to clump up or under the influence of gravity in the same way, or it doesn't form structures in the universe. But again, we'll get into each of these in a little bit more detail. So I'm going to sort of outline how the sort of measurements worked that led to the discovery of putting this pie chart together. And then we'll talk a little bit about more how we can approach trying to gather some more information about it. So the sort of first distinctive evidence that dark matter existed, that there needed to be some other source of mass clustering in the universe, making up part of galaxies, came in 1970 through observations that Vera Rubin, who's like one of my personal heroes, made observing the rotation, the orbits of stars and galaxies. And so what she discovered is that stars orbiting galaxies are moving faster around the galaxies than you'd expect if all of the mass of the galaxy just came from like the matter that we can see through starlight and the gas emitting visible radiation. And so there's a little thought experiment here to understand why this would be telling us that there's more mass here. So I've done this before where I actually hold a yo-yo and swing it around, but I couldn't find a yo-yo, so I'll have to do, thought experiments are big in physics. So our thought experiment is we're going to imagine swinging a yo-yo around on a string, using a yo-yo in a very incorrect way to use a yo-yo. But so when you're swinging the yo-yo around on a string, it's going in a circle, and it's a tension on the string, and you're holding the string that is keeping it from just flying out across the room and making it a much more hazardous thought experiment. And so if you're swinging slowly, there's a slower velocity, you don't have to hold onto that string very hard, you just swing it around leisurely. But if you start spinning faster, you're going to have to hold on tighter. There's going to be more tension in the string required to keep it going in a circle and not just flying off. I see a question in the back. Oh, I think let's stick with the thought experiment. I appreciate it. I'm impressed. Okay, but you can kind of intuitively think you're swinging something around. If you start stringing it faster, it's going to take more force to keep it going in a circle and not flying off into the room. And so this is a universal property of basically any kind of circular motion. To keep something moving in a circle, the faster it's moving, the more force it takes to keep it in an orbit in a circle. And when we look at stars moving in galaxies, it's not tension on a string holding the stars moving around the center of the galaxy. It's the gravitational force of the star being attracted to all of the matter that's inside its orbit. So the more mass that there is inside the star's orbit, the more gravitational force that mass is providing, and that means the star is able to orbit more quickly. And so what Vera Rubin did is she measured the rotation speed of stars moving further and further out from the center of many different galaxies. And if most of the matter, the mass in the galaxy is the visible mass, and this is how things work in our solar system, where most of the mass in the solar system is in the sun, as you look at planets further and further out in the solar system, their velocities are moving slower. And what we find, or what Vera Rubin found looking at these distant galaxies, instead of seeing like this gray line, seeing the velocity go down as you move further from the center of the galaxy and further from most of the visible mass, you actually see, and probably could adjust this cartoon a little bit, it actually kind of flattens out. You don't see that turn down there. And to explain that, the thing that can explain that is if instead of most of the mass being in the visible part of the galaxy, the structure of a galaxy is actually a large sort of, we call it halo, a large sort of spherical blob of invisible gravitating matter with the visible galaxy kind of just taking up a little bit of space in the middle. And so in this case, as you keep moving further out in the visible galaxy, you're getting more and more mass inside its orbit in a way that actually ends up predicting that the rotational curve of stars as you move out in the visible part of the galaxy stays flat instead of decreasing. So this was very unexpected. It was pretty compelling. There had been some hints before Vera Rubin's observations that maybe there was some invisible mass needed to explain how galaxies are moving in galaxy clusters, but this was the first really sort of smoking gun compelling evidence that there needed to be something there. And since then, there's been a lot of other observations sort of supporting this idea that there's about 5 times as much invisible dark matter in the universe than ordinary matter. So I'm going to move on to talking about dark energy. So remember, this is the biggest piece, the 70% of the matter and energy in the universe is this thing we call dark energy. And the evidence of dark energy is related to our observations of how the universe has been expanding over time. So the fact that the universe is expanding is something that we've known since the 1920s. This is one of the major discoveries of Edwin Hubble when he was measuring the velocity with which distant galaxies are moving away from us. He realized that the further away a galaxy was, the faster it was moving away from us. And this was true in all directions. And the way we understand that is that space itself in the universe is expanding uniformly. So in this illustration here, the image is like you can picture galaxies on the surface of a balloon that's being blown up. There's another analogy you can make of, you think of like raisins in a loaf of raisin bread as the bread rises. And so there it is. The reason this causes this relationship between distance and velocity is because, you know, if a galaxy is twice as far away from you, there's twice as much space between you and that galaxy. And so twice as much space to expand means it's going to be, that expansion is going to cause it to move twice as fast away from you. And so, and another important piece of information when we're thinking about how we know how we came to discover the need for dark energy is this idea of look back time. So light travels at a finite speed. So when you're looking at objects in the universe, the further away an object is, the longer it took the light to get to you. So it's carrying information about what the universe or what that object generating the light looked like at earlier times. So like you can also translate this into distances. So like the sun is 8 light minutes away. That means, you know, the light we're getting from the sun left the sun 8 minutes ago. Or like the nearest star to us is about 4 light years away. So when we're seeing the light from it, we're actually seeing what that star was doing 4 years ago. And as you go further and further out in the universe, you're, you know, gathering information about things at earlier and earlier times. This means that if we can look at how objects or distant galaxies are moving away from us as a function, and how that depends on their distance from us, we can learn about how the expansion rate, how fast the universe is expanding has changed over time. And so we do that using, and this is really not showing up here. The other lines are darker than this line, I promise. So this is something called a Hubble diagram. And what it is it's showing a relationship between distance on the vertical axis. So going further up on the plot here is objects that are further away, which means they have information about earlier times. And then lower down, that's nearby objects, so more recent information. And we plot this against velocity, which we can measure if we can observe the like the colors or the spectra of objects. So when things are moving away from you, the colors that they would emit, the wavelengths of the light that they're emitting gets red shifted. So it ends up looking redder than it would be if you were just measuring that light directly, because of something called the Doppler effect. So this is a thing that affects any kind of light or sound wave coming from a moving object. So the color tells us about the velocity of a distant galaxy, and you can use different methods to, well, the distance measurement is tricky. So we, in practice for this, and the discovery of dark energy was made using observations of a type of supernova. They're called type 1A supernova. The important thing to know about them is that they're a type of explosion that happens, that basically always happens at approximately the same intrinsic brightness. And, you know, you can think of, if you're looking at like street lights along the road, if all of those lights are the same brightness, you'll notice that the ones that are further away will look fainter because they're further away. And so we can use the apparent brightness that we observe of these uniform brightness supernova to measure their distance. So we call them a standard candle, which is what this little illustration in the lower left is illustrating. So we have this population of supernova. We can like keep a careful look at many galaxies for when these things go off. And if we can measure the color, the spectrum of the galaxy they're in, and then the brightness of the supernova, we can get both a distance and a velocity, and we can put it on this plot. The line that's very hard to see in the room is just a straight line, and it says constant expansion. So if the universe is always expanding at the same rate, it just however much space is between you and a distant object dictates how fast it's moving away. And that will be the same for all objects you're observing if the universe has always been expanding at the same rate. Okay. If that rate has changed over time, we'll see deviations from a straight line on this kind of plot. And what we expected so it was in the 90s, there were a couple teams working to measure this precisely and look out far enough that you could actually see deviations from this straight line. And what everyone expected to see was that the universe's expansion rate would be slowing down over time. So the theory we have to describe gravity, which is Einstein's theory of general relativity, that theory relates the behavior of space-time, which includes the expansion of the universe, to the matter and energy in that space-time. And so the amount of matter and the stuff in the universe will influence its expansion history. And if the universe is just contains matter, dark matter, ordinary matter, any kind of matter that feels gravitational forces, and gravity works according to general relativity, you would actually expect the expansion rate would be slowing down over time. You can kind of think of like gravity as sort of pulling on as a brake against that outward expansion. And so as a result, what you'd expect to see in this kind of plot from the expansion slowing down is that as we look to objects that are further away, so information from earlier time, if things have been slowing down, it means the expansion was faster in the past. So for a given time, so if you pick like a horizontal slice of this plot, you're going to expect that the galaxies that are further away are going to be moving a little bit faster than they would if everything was expanding at a constant rate. So we see this line curving a little bit down below the constant expansion. And what these teams, there are two different teams that made these observations in the late 90s, were surprised to find was that things are not slowing down. The expansion is actually speeding up and has been for the last like 2 billion years or so. And this was very surprising. It's surprising enough and a notable enough discovery that the teams that discovered this got the Nobel Prize for it in 2011. And I like to think of it as like, it's about as surprising as if you threw a ball up in the air and instead of seeing it fall back down, it just zoomed off in some direction. So in the same way that you'd expect that ball would need some explanation, to explain this accelerating expansion, there needs to be some source of energy driving that acceleration. And dark energy is the name we give to whatever that is. So we don't really know what it is. The simplest explanation or the simplest thing that could give us this behavior would be if dark energy is something called a cosmological constant, which is basically an energy density that's just intrinsic to empty space. And so that would mean that there's a uniform energy density everywhere in the universe, constant in time, same everywhere in space. That's what we mean when we say a cosmological constant. And this type of substance, this type of energy would give you this kind of accelerating expansion that we see. And just to give you a sense, like, this is really weird. And so we can do another little thought experiment is like, if you have some like matter in a box, say like some marbles or just atoms of some kind, and you double the size of the box, you increase the size of the box, the number of atoms in the box, the amount of matter is not going to change. And so that means if you increase the size of the box, the density goes down because density is mass divided by volume. Now, if dark energy acts like a constant energy density, that means you like double the size of your box of dark energy and you have twice as much dark energy because the density stays the same. And so the total amount of energy sort of is somewhat unintuitively not really conserved when we're working in this framework. And so basically it has to behave like no other substance we're familiar with. So this cosmological constant could explain the accelerating expansion, but we don't necessarily think that's the whole story. It is possible there could be some new type of field or substance in the universe that we need to add to our description of it. Or maybe this could be a hint that our theory of gravity, general relativity, needs to be extended when we want to describe the really large scales of the universe. And so these are things we would like to know more about. And in the same way as like dark matter, we can constrain how much of it and how it's distributed based on how it influences visible matter. We can learn about dark energy based on how it affects things we can observe and try and constrain its properties and test whether is it really a cosmological constant, or is it does it have do its properties have some time dependence? Are there any hints that maybe we need to change our description of gravity in certain environments? So, all right, so I'm shifting gears a little bit and just kind of trying to put this all together and talk about how we might approach trying to learn about this with observations of the universe. But I guess this would be a good point to pause. And does anyone have any questions?
What's this poor guy?
That's where we are. Yeah. Yeah, so this is, so I'm trying to sort of, oh, I see, is that a question in the chat?
Yeah, go ahead.
Me?
Did you have a comment?
Oh, I thought I saw something in the chat.
There's a couple. You want to deal with them?
Maybe I'll take like one or two and then we can.
Okay. A few years ago, I read that the value of the Hubble constant was different depending on the measurement method, about 68 or 73 kilometers per second per megaparsec. These are significant differences. Has this been resolved?
The answer is no, it has not been resolved. So yeah, I guess this would actually feed into this slide pretty well. And so maybe I'll just say a little bit to kind of answer, well, at least put that into context a bit. So this sort of pie chart picture description of like how much of the matter is made up of different substances and like different assumptions you can make about what dark energy is or how dark matter behaves or what type of particle it is. You can combine these with a few other ingredients, one being our theory of gravity, which in our standard picture is general relativity, and one being some information about how fast the universe is currently expanding. So you can kind of think the dark matter, dark energy tells you how expansion has changed over time. And then you also, if you want to describe the whole expansion history, you put in the current expansion rate. And this Hubble parameter is a parameter in our model that describes this current rate of expansion. And yeah, roughly speaking, you can constrain these parameters, and we'll talk a little bit about how we do this in certain contexts using different kinds of observables. And this Hubble tension that people, the sort of the buzzy name for it is different measurements of this parameter describing the current expansion rate give different results. And yeah, it's still an open question. So I think maybe we can come back to this towards the end because I'm gonna talk about some stuff that maybe put that in context. Yeah.
Okay, just to be clear, universe is expanding, space itself is expanding, dark energy, whatever it is, increasing. So the dark energy is driving the expansion, or is it the other way around, or are they both the same thing?
Yeah. So yeah, oh, okay. I can repeat the question. Yeah. So the question, and this will be a good chance to make sure I follow. You were asking whether dark energy is driving expansion of the universe or right. Yes. So yeah. So there's definitely a relation because yeah, as space expands, the matter density gets diluted and the dark energy density stays the same. So over time, actually, dark energy is going to become an even bigger and bigger and bigger piece of this pie. And so the acceleration will become more dominant as the universe evolves. So there's kind of a positive feedback loop happening. So the universe could be expanding even without dark energy. Like you have the Big Bang, the sort of explosion, well, this initial kick that all of space expands out from a singularity at early times. Easy to think of it as an explosion, not quite a correct explanation, description, but yeah, the thing that dark energy is driving is the fact that is accelerating. So it's like stepping on a gas pedal for that expansion. So I would say they're interrelated. That's a good question. All right. So yeah, we can talk about with these models, these ingredients allow us to describe the expansion history of the universe. And this is a little cartoon sort of schematically describing the fact that the universe started out being very small and dense, and it expanded over time. And the fact that the like little tube here kind of flutes out at the end is meant to represent that expansion is speeding up at late times in the universe. Sort of another big category of things that this model can describe, if we add one more ingredient of small density fluctuations in the early universe, we can also use the same ingredient to describe the evolution of structure in the universe. So in our model and our understanding of the universe, things started out at early times that the universe was very uniform. One location in space looked very similar to all other locations in space, and fluctuations in density were very, very, very tiny. Then over time, gravity causes mass to attract mass. So if you have a tiny little bit of more matter over here than over here, gravitational force is going to pull matter into that overdensity in the locations with more mass. And that will continue over time and cause matter, like tiny fluctuations in density, to grow, becoming more massive, and matter clumps up over time. So eventually you end up with the universe we have today, which is very non-uniform. We have locations in space that have galaxies in them, or groups of galaxies, and planets, which we're all very happy about. And so sort of the major sort of things that we can predict with our model, and when we're talking about the universe at very large scales, is expansion history and the evolution of structure growth. And we can track different observations of those structures from the early universe. So, and through the observations we can make of the distribution of galaxies today. And that's sort of where most of my work focuses. So a key thing here, and that kind of maybe follows from some of these things that we're saying, is the structure in the universe, or the distribution of matter on large scales in the universe, depends on basically all the ingredients of that model. So this image here is showing 3 time steps of a simulation of a distribution of matter shown with this sort of purple-blue cloud, going from a box where density fluctuations are very small on the left, so it's mostly kind of uniform, it's not very clumpy, to gravity working, to having these like clumpy filamentary structures in the image on the right. And the way and the rate at which the matter clumps up, and thus the resulting like statistical properties of how matter, like what that filamentary structure looks like, is going to be sensitive to a lot of different kinds of fundamental physics. So it's going to be sensitive to how big and were the density fluctuations in the early universe, and how were they distributed. It's going to be sensitive, maybe somewhat obviously, to how gravity works and what the matter is like doing that clumping. So if you change the properties of matter, if you let dark matter have some interactions with other matter, that would influence how this clumping looks and what the structure looks like eventually. So the way gravity behaves, what the matter doing the clumping is like, will affect this. And then somewhat a little bit less intuitively, the structure formation will also be sensitive to expansion history, and through that, the amount and properties of dark energy. And the way to think of this is that the expansion of the universe acts almost like a friction to the formation of structure. If you're stretching space out, you're kind of pulling galaxies apart from one another. And so that's sort of counteracting what they would want to do just from the force of gravity, which we fall together. So you can kind of think of expansion and gravity as sort of competing forces for gravity wants matter to clump up, expansion wants that clumping to slow down or stop. And so if you have, say, more dark energy in your universe, more dark energy means more accelerated expansion, which means faster expansion, which makes it harder for structures to grow. So we can use the rate at which these structures will grow to tell us about things like gravity, dark matter, and dark energy. Yeah.
Does that matter?
That's a good question. Oh, yeah.
Thanks.
So the comment was that this looks anti-entropic, so it looks like it's going into something that's like more ordered at the end than you start out at the beginning. I'm not 100% certain. One thing that might explain where entropy is going is when matter falls into overdensities, it tends to pick up velocity, so everything is kind of heating up in a certain way. Yes, I'm not exactly sure how that like trades off. I think on large scales cosmologically, like I'm remembering from my like cosmology class from a while ago, it's like you can do some like entropy for volume ends up actually getting conserved when you're tracking what kinds of particles are around. But I don't know. Anything beyond that, I'd be hand waving and half remembering. But yeah, it's a good question. All right. And then I think it's good to maybe take a moment to, I'm talking about large scale structure. And I will say that as a cosmologist, what I think of as large and small scales is not the same as even other astronomers. So I don't know, we'll see if you, an astronomy joke that is maybe not that funny, but I like it, is how you can tell if somebody is an astrophysicist or a cosmologist is ask them, is a galaxy big or small? And as a cosmologist, I would say galaxies are small. But yeah, just to put this in context, I have a little table here that lists in a couple different units, distances, different distances that we might think about in astronomy. The first column being a light travel time. So I mentioned earlier, the sun is 8 light minutes away, and the nearest star, Alpha Centauri, is about 4 light years away. You can translate that into distances in kilometers, which these are such big numbers, it doesn't mean anything to me. If it means something to you, great. Really big numbers. We're working in astronomy. The units that I mostly think in terms of cosmology is parsecs, or particularly megaparsecs. Roughly speaking, a parsec is about 3 light years. But just kind of walking out in distance, we've got our stellar neighborhood is measured in light years. If you're trying to look towards the center of our galaxy, the Milky Way, you're starting to talk about thousands of light years. So the center of the Milky Way is 26,000 light years away. If we want to look to the Andromeda Galaxy, which is our nearest neighbor, we're seeing the Andromeda Galaxy as it was about 2 million years ago. It took that long for the light to get to us. So even, this is a relatively close galactic neighborhood, and it's still like, I don't know, like I personally can't like intrinsically understand these distances, but you put them on. We all think in different contexts here. And then what I'm talking about as large scales or cosmological scales is things bigger than about 30 million light years, or in cosmologist units, 10 megaparsecs. So I'm probably going to trip up and be a little jargony later. And so if I refer to something as small scales, I'm talking about anything smaller than about 30 million light years. And so this is sort of what we're talking about when we talk about the large scale properties of the universe. Oh, okay. Got a little bit of a lag in my slide. Okay. So we want to learn about, so I guess, yeah, first thing to say is I talked about how the properties of structure in the universe, the distribution and evolution of matter density fluctuations, that's sensitive to a lot of different fundamental physics. And so that means if we turn that around, if we can measure that structure, we can measure the distribution of matter and how that's evolved over time. That means we can use that to test models for what dark energy acts like and what dark matter acts like and how gravity behaves. And so we want to go and measure large scale structure to learn about dark matter, dark energy, gravity. And here we run into a challenge. So the thing that we're able to model well when we're making predictions for how structure in the universe would look like is we have a lot of good computational tools, both pen and paper or in practice, a lot of like software tools that we can predict pretty exactly what we expect the dark matter to be doing. It's very like dark matter is a strange, mysterious thing from like an intuitive point of view, but from a calculational point of view, the fact that it basically only interacts through gravity makes it simple. Galaxies, gas, that's complicated. You have to worry about pressure, you have to worry about magnetic field, you have to worry about stars exploding. Dark matter, just gravity. So our models are really good at predicting the behavior of dark matter, which conveniently for us makes up most of the matter in the universe. So that's good enough for describing most of large scale structure we're worried about. But the tricky thing is it's invisible. So that presents a challenge. And so instead of, we want to know about the total distribution of matter in the universe. And what we have as a handle is looking at the visible matter, so galaxies. And this slide is another image from a simulation. And what it's showing in the grayscale lines is the distribution of dark matter. So the darker grays and blacks is the high density regions of dark matter. light gray is low density region of dark matter. And the simulation has these sort of gold points on it showing where galaxies are. And so you see that the galaxies form only like in the really high density region. So we're sort of at the knots and high density points of these filaments. Yeah. And so we're looking to use the relationship between these galaxies and that underlying matter, observations of galaxies, to learn about the dark matter. And so this is, and you can make an analogy here where it's like if you want to study the distribution of people on the planet Earth by using satellite images of the Earth at night. So you can kind of see like the city lights. You're not exactly seeing where all the people are, but you can kind of see tracers of where they reside.
As an additional scale, just a few million light years, so again, when Andromeda here, would the size of that be Milky Way-ish, the size of that, or does the scale translate in that way?
Yeah, I believe so. I don't know often. So I know that this simulation is of a really big galaxy cluster. So yeah, I guess, yeah, if Andromeda is like a megaparsec away, a couple million light years, yeah. So I guess, yeah, Milky Way and Andromeda would be like two of these little specks. Yeah. So there's some scaling based on like how you observe things far away, but I think because this is a simulation, as long as I copied the scale. I think I drew this little bar just kind of estimating based on the size of the galaxy cluster. So generally galaxy clusters tend to be a few megaparsecs across. And so I've kind of, so this is a schematic scale bar just to kind of give you a sense. But yeah, it works the same way. Yep.
So, according to that, would you anticipate that there is a filament, a dark matter filament, between us and the Andromeda galaxy? So we're lying on a filament, probably because we're in a galaxy.
That's a good. So the question was, would this imply that there would be like a dark matter filament between the Milky Way and Andromeda? Possibly. I'm not sure offhand if people have studied this explicitly. I think it's kind of hard to see from where we're at, but I know people have studied like pairs of galaxies or galaxies that's like that you can sort of see the whole, like Milky Way is hard to study because we're inside of it. Though admittedly, I am not an expert in like Milky Way astronomy, so there might be research in this that I'm not familiar with. But I know people have done sort of clever things where they stack distant like images of distant galaxies so they can kind of add up some noise and sort of look for hints at like filaments. So people have studied this and they can categorize galaxies in big sets of observations of whether you think it's in a filament or not, and look at like, do galaxy properties look different if they're in galaxy clusters versus filaments versus voids? Because, you know, if they're not interacting with as many neighbors, there might be different galaxy evolution properties. And I don't know. Yeah, so the question is, where did the filaments come from? So this will actually happen. So the way they start out these simulations and is that you don't have to input anything about the filaments. You just start out with a random field, so like random fluctuations, just like noise and initial density, and just the way that gravity will cause sort of blobs of matter to collapse ends up giving you these filaments. And I think if you like, you can tune some different interactions and you could get things that kind of look like soap bubbles or something. But this is just, it happens to be like, if you have a blob that's an overdensity, it'll tend to collapse along the skinnier direction first and then the longer one. And so as a result, you get these like filamentary structures. And then, yeah, the galaxies, the ordinary matter is a small fraction of the total matter. And so it tends to follow the dark matter or behave gravitationally in a similar way and sort of basically settle in the high density regions to form these galaxies. So the galaxies trace these filamentary overdensities because the matter that makes the galaxies is also taking part in like the growing overdensities. Okay. So we want to observe a bunch of galaxies to try and map these structures, and the type of experiment or effort that we use to do that we call a galaxy survey. So these are like systematic efforts to observe many, many galaxies in a uniform enough way that you can use them to like infer properties of the underlying matter density. And you can sort of broadly describe galaxy surveys into two categories. Excuse me. So the two categories are spectroscopic surveys and imaging surveys. And I think I saw it briefly in the chat. Sorry. Earlier, somebody had asked a question about the dark energy spectroscopic instruments, or DESI, and that is an example of this first type of galaxy survey. A spectroscopic survey, the way this works is you point optical fibers at individual galaxies, and with that optical fiber, you can gather a bunch of light from each galaxy and make a detailed measurement of the galaxy's spectrum. So like how bright the galaxy is in different wavelengths of light. And so that's what this picture here at the top is showing. It's, yeah, the labels are not visible on this slide. So, the vertical axis is flux or brightness, and the horizontal axis is the wavelength, so the color. And you can see when you're measuring the galaxy color, you see some absorption lines and maybe some spikes from emission that correspond to different interactions that the light might have with different gases and atoms and things in the galaxy. And the wavelengths of these lines will be the same in a distant galaxy as they are in our lab, so we can match them to absorption lines that we know about and can study on Earth. And that means, and then we can compare that to what colors we see them in the galaxy to get a very precise measurement of how red shifted or how shifted that galaxy's light is toward by its motion moving away from us. And we know that galaxies that are further away are moving faster, so we can use these precise measurements of color to get a precise sort of three-dimensional coordinate of how far away the galaxy is from us. So these spectroscopic surveys, you're looking at galaxies on the sky and you know where they are because you're pointing your optical fiber at them. And then the colors, the spectrum gives you that third coordinate, where how far away is it? And so you can put these things together to make a nice three-dimensional map of these galaxy positions in space. And yeah, there's one, well, there are several examples of these kind of surveys. If you've heard of the Sloan Digital Sky Survey, or the BOSS, which stands for, I have some guesses of what I think the acronym stands for, but these are different survey names that exist. That's sort of like the state of the art that has the data out publicly so far. DESI is a very exciting experiment that actually just turned on about a year ago. Data is coming in, and like even with like a year of observations, I think it's surpassing the number of galaxies that all the previous experiments have measured. So I'm going to be actually focusing in the talk mostly on the second type of survey, imaging surveys, because that's what I work on. But just to note that these are two different ways of gathering information about galaxies. Imaging surveys, as the name might suggest, is that instead of pointing an optical fiber and measuring a spectrum really well, we use basically a giant digital camera on a telescope to image the sky. And given this, instead of measuring precise spectrum from each galaxy, we have to infer the colors by looking at how bright the galaxies look in a few sort of fairly broad color filters. So instead of seeing all of these individual lines here, we kind of chop this up into like 4 or 5 big chunks. And we can say it's this bright in this part of the spectrum, this bright in another. And so ultimately, when you're using these imaging surveys, your distance information, which comes from that color, is going to be very uncertain. But what you can measure that the spectroscopic surveys don't get at is if you have an image of a galaxy, you can measure its shape on the sky. And also, because you're not measuring these detailed spectra, you can actually observe more galaxies because you don't have to spend as much time gathering light from each individual galaxy. And there are several ongoing imaging surveys. The one I work on, called the Dark Energy Survey, is in that list. And there's also, there are a number of upcoming surveys that will be turning on in the next couple of years that will be even bigger and better. And so one that I am involved in is something called the Vera Rubin Observatory Legacy Survey of Space and Time, named for Vera Rubin of the dark matter discovery. So there's a lot of observational and experimental effort to measure the distribution of galaxies using different methods. we're going to be talking mostly about imaging surveys, again, because that's what I work on. And the key thing to know, or that makes imaging surveys particularly interesting for studying the distribution of matter in the universe, is the fact that measuring galaxy shapes lets you measure the signals of something called weak gravitational lensing. So gravitational lensing refers to the idea that gravity will deflect the path of light. This is something that is predicted by general relativity observations of the deflection of light around stars near the sun was one of the first experimental tests that verified that general relativity did in fact work and work better than Newtonian descriptions of gravity. And when we're thinking about it with galaxies, the thing to think about, or what this cartoon is illustrating, is we imagine we're looking at a set of very distant galaxies, so these guys here. And if there was nothing between us and those galaxies, we'd observe them with a certain set of shapes on the sky. But there is stuff between us and distant galaxies. If the galaxy is far enough away, that light's going to be traveling through a bunch of this filamentary large-scale structure, these clumps of matter, which have gravitational fields that is going to deflect the light along the line of sight. So if you have a big blob of matter between you and those galaxies, their light's going to get a little bit deflected in a way that in practice distorts the galaxy shape. So if you have a blob of matter between you and some galaxies, it's like you have a lens between you and the galaxies. It will distort the images you see. And what it does ends up doing is it introduces alignments between the galaxy shapes. And I say, so generally you can kind of think of the galaxies, mostly their intrinsic shapes will be pretty random on the sky. But then galaxies that are near one another on their sky, their light's going to be traveling through similar structures, similar gravitational fields. And so they'll experience similar kinds of lensing distortions. And so the effect of this lensing is that you end up having the observed shapes of these galaxies looking aligned with one another. And the more aligned those shapes look, that tells you that there's bigger clumps of matter, so stronger gravitational pull at deflecting the path of that light. And so we can measure those alignments to sort of infer properties of the clumps, or how clumpy the matter between us and those galaxies are. And a thing to emphasize here, this is a very exaggerated picture in the cartoon here. In practice, the distortion of the galaxy shapes is a really tiny effect. So when you look at a blob of light on the sky, you can quantify its like ellipticity, or the extent to which it's an oval and not a circle. And lensing will just change that ovalness by some extent. And like if you can measure that, the change is 0.1%. So teeny, teeny, tiny effect. And so it's small enough that if you're observing just one set of galaxies, or like a handful of galaxies, you would have no way of knowing, like, is there lensing causing alignments here, or is this just the shapes these galaxies are? And so this is something that, to be sensitive to this, we really have to go into like large number statistics. We observe very, very large numbers of galaxies, which we can check the alignments of these shapes enough that the sort of random shapes of the galaxies will average out, while the alignment from the weak lensing gives us information about structure. And so the experiment that I'm going to dig into talking about a bit now, the dark energy survey, is particularly aiming to do this. And so the analysis that I'm going to be talking about is based on measurements of 100 million galaxy shapes. So we're talking big numbers here. And you know, with those big numbers, there's a lot of observing time. So the survey is operated out of the Victor Blanco telescope. It's a 4-meter telescope at the CTIO Observatory in Chile. So, well, this very hard to see map is a map of South America, just pointing out that the observatory is in Chile. And this observation, or this photo on the left, is from an observing shift I did back in 2017. So I'm mostly a theorist. I mostly do data analysis. But to do this survey, we did 756 nights of observing over 6 years. So they even let theorists go push buttons on the telescope to do observing shifts. So this was a very special experience for me. Like to get there, you fly to this little beach town, and then you take a van 3 hours up into the mountains and you stay in an observatory. And it's really quite remarkable. And like, I don't know, maybe you all think about telescopes slightly more, well, in different ways than I do, but the, 4 meters sounds big. It's a big mirror. But I think before I actually sort of went to visit this telescope dome, I didn't quite fully absorb like how big that meant the building that the mirror and the telescope would have to be in would be. And so you can kind of see in this picture, it's a telescope dome. It looks like you expect to see, but this over here, this little rectangle, you can see there are doors here. So this is how you get into the building. So this is a really big structure. So like I'm in the picture in the front here, but I'm pretty far in the foreground. And yeah, to take that data and to analyze it and get physics information out, it is really a collaborative effort. There's something like 400 active scientists doing different kinds of science with this data. Collaborators there are people at a lot of different international institutions. So we were doing a lot of Zoom meetings before everyone else in the world was doing a lot of Zoom meetings. And we continue to do a lot of Zoom meetings. People associated with the Dark Energy Survey actually built the camera on the telescope specifically for this survey. It's creatively named as the Dark Energy Camera. So this is a picture of the telescope, again, with me showing off that I got to go see a telescope. And in it, there's this black cylinder towards the top of this, and this is the camera. So this is a giant digital camera, the CCD chip in there, which would be, like that big in a DSLR or something, is about 3 feet across. And it was designed specifically to be extra sensitive to red light. And the reason you want to do that is because we're looking at galaxies that are very far away. Their light tends to be redshifted because they're moving away from us. And so to be able to see distant and very faint galaxies, you want to be more sensitive to that red light. That was the Dark Energy Camera was mounted on the telescope back in 2011. And I kind of mentioned earlier, lots of nights of observations. They completed in January of 2019. And since then, and like during then, we've been hard at work to analyze that data. And again, I'm kind of talking a little about it already. This is from a collaboration meeting a few years ago. But this is one collaboration meeting we have. We usually all get together twice a year, sometimes in person, sometimes virtually. In 2020, very clearly. That's a good question. Yeah, I know I found myself in here, but I don't know. We can come back and do a Where's Waldo later. But yeah, like I do have to say, like, going to the telescope was great, but also like a really rewarding thing about kind of working in this kind of endeavor is to be able to get to know and interact with people from all over the world who are interested in this, kind of science. All right, so I'm going to walk through a little animation to think about how we conduct the survey. So this is an image from the Dark Energy Survey. So it's not just one exposure, it's several combined to give you this false color image. So on our camera, we have 5 different color filters that we're able to take pictures in. And in this image, these little blobs, well, there might be a star up here, but these are mostly galaxies, all of these little blobs. And different colors, they might be sensitive to how far away the galaxy is or also the properties of the galaxy itself. That's a small piece of what we get in a single exposure in the telescope. So we've got, I think there's something like 77, 72 CCD chips in this like 3-foot big disk that we detect the light with. And each exposure in this, so we can see an area of the sky that's a few times wider than the full. So this is a big field of view for this kind of telescope that can see this deep. And we do, I think, by tiling different exposures of this sort of hexagon-shaped observation, we can tile in the sky and we observe basically about 1 million galaxies a night. And we can tile that, covering patches of the sky. Sometimes this animation is a little glitchy. Oh. Well, it's supposed to dramatically fill in, and we fill in a shape covering a part of the sky that is 5,000 square degrees. So that's about 1/8 of the total area of the sky. So this is why we need that many nights of observations, and that's how we can gather data about 100 million galaxy shapes. I think our final data set will have more like 200 million, But we analyze it in stages. So the results that I'll talk to you about today are from analyzing the first 3 years of the data. So covering this full survey footprint, but only at about half. We tend to image every patch of the sky 10 times in each of 5 color filters. So 50 images. By taking multiple images, you can combine them. So any sort of random noise will cancel out. And then you can get clearer images of the galaxy shapes and colors. So we say the year 3 analysis, and it's the first half of the data. We're actively at work doing the final data analysis. And so I'm gonna shift into talking a little bit about how we approach that data analysis, but I'm happy to stop and take a question or two.
I have a question.
Yep.
As we learn more about dark matter, is what we've learned thus far consistent with the existence of the singularity, the Big Bang?
Yeah, so the question was whether, as we learn more about dark matter, if that stays consistent with the existence of a Big Bang. I would say that, I guess the important thing for the expansion of the universe is less like the detailed properties of like what type of particle the dark matter is, and more just like how much of it there is, because the amount of matter will influence how the expansion of the universe changes over time. And so far, we've had a pretty consistent picture in the like dark matter making up about that same size of the pie chart. So it doesn't dramatically change the picture of the Big Bang. And then I saw you had a question as well.
James Webb. Are you using James Webb in the dark energy survey?
We are not. There are some kinds of science that people do also use dark energy survey measurements for, that JWST images can be helpful for. It's less this sort of this large scale structure study. So here, we're really relying on this really big field of view to be able to do this big map of many, many galaxies. And JWST really specializes in really sharp, well-defined images of a very tiny field of view. So like, I'm not going to back up through that animation because we might get stuck there. But like, the DES field of view is something like 2 degrees on the sky, which is big. And I think I actually looked this up the other day, but I've already forgotten. JWST field of view is something like a few arc minutes, I want to say, so much smaller. So something that people do with DES and that you could do with other galaxy surveys is you can search these really big images for systems that might be interesting to follow up on. So I'm talking here mostly about like weak gravitational lensing, like tiny distortions of galaxy shapes. But there are very rare systems where you have a really big, massive thing in front of another galaxy, and you get something called strong gravitational lensing. So these really cool arcs and distortions. If you look at the first like press release photo from JWST, it's really visible there. And so I do have some collaborators who search like DES images and do some like sort of machine learning related searches to find candidates for these strong lensing systems that you could then like follow up with JWST to get really nice images of to measure the properties. So there's some complementarity for the kind of science that I'm talking about here, where you're trying to map the large scale structure. You're not really able to make much progress there without these like big fields of view. So the successor to DES, we've got this 2 degree field of view. The Vera Rubin LSST survey is using a camera, which I don't remember the field of view, but it's even bigger. And they're basically going to be able to image the whole sky that they can access from their latitude every 3 nights, which is wild. And so, when you're doing that, in addition to being able to make really good galaxy measurements, they're going to be really good at finding things that move. So like asteroids, and like people do use the DES data because we're imaging this big area 50 times each over 6 years. There's a team that searches it for like distant solar system objects. So that people have discovered like a dwarf planet, or some of my collaborators discovered like, I think like the biggest comet that people have just like, it wasn't visible to naked eye, but this really big comet. So that was, so there's a lot of things you can do with this kind of data, and some of it ties in more or less with things like JWST. More question in the back? Okay. Yeah. Yeah, those are questions near and dear to my heart. So the questions are roughly, does cosmological constant dark energy, would that mean the universe is expanding forever? Second part, does this accelerating expansion point towards maybe laws of physics don't work the way we think at large scales? And yeah, so I guess the answer is yes to both questions. So yeah, if the model that we have, this description of cosmological constant dark energy, gravity behaving under the description of general relativity, if you follow that through to a conclusion, that tells you, all right, dark energy is causing the expansion of the universe to accelerate. As the universe expands, the fraction that's made up of matter dilutes. So dark energy dominates even more. And you get this feedback where you expand and expand and expand and could just expand forever until the universe is really, really dominated by dark energy and matter is all very spread out and dilute. If dark energy has some other time-dependent properties, that could change. And yeah, one of the things we really are interested in terms of studying dark energy, because its behavior is so counterintuitive, we haven't quite been able to tie it to like quantum understanding of forces and things, that we are very interested in, like by constraining its behavior and its properties really precisely, if we can find if and where that cosmological constant description breaks down, that might give us hints to give a more like fundamental description of like, you know, do we need to extend general relativity on cosmological scales in a similar way that general relativity expanded Newtonian physics? All right, I'm just have an eye on the time. Or we still have,
Oh, yeah.
Okay.
Let's just,
okay. All right, so just thinking through, remember, you know, with our galaxy survey, our goal is to measure the distribution of matter in this cartoon that's meant to be illustrated by these darker blue squiggly lines. And what we're observing are light from galaxies, which I'm showing in yellow and red here. And the analysis that I work on in particular uses two different approaches to a couple different observables to learn about that structure. One, as I mentioned earlier, we use the distortion of galaxies' apparent shapes due to weak lensing. So we can say, pick a sample of very distant galaxies, which I've colored in yellow in the picture, and measure their shapes and look at, in particular, how the relative alignment or randomness of their shapes depends on how separated they are on the sky. And the, you know, more alignment and the angular scale, or how that depends on how separated galaxies are on the sky, will tell you about how like clumpy the matter is causing that lensing. We can also pick another sample of galaxies that are a little bit closer to us, that are somewhat reside in the structures doing that lensing. And we can use the fact that galaxies form in high density regions. So the distribution of those red galaxies in space traces the underlying matter. And so we can make a measurement that basically asks, how likely is it that I find two of these red galaxies separated by a certain distance on the sky compared to what you get if it was just a random distribution? And that gives you sort of a statistical description of how clumpy is the matter. That's all what we're going for. And I guess I think to put this into context, when we want to so we're going to test our models of dark energy of gravity by making predictions for our observables. And the predictions we can make are not, I expect to see a galaxy right there and one galaxy here and one with this shape. We can only make sort of statistical predictions of, I expect the universe to be this uniform or this clumpy. And so instead of anytime you try to compare a model to data, we're not comparing it to measurements of all 100 million galaxies at once. What we do is we take this big catalog of galaxy measurements and we create something we call summary statistics. So sets of numbers, and in practice, we measure about 400 summary like numbers from these sort of clustering, like how probable is it that I find two galaxies separated by this angular scale in the sky or this one? And that's where our model meets the data. So that's sort of the context of what these little lines are illustrating here. And then the third way we can use these same observables is we have the red galaxy positions, the yellow galaxy shapes. we can look at the relationship to those. Like, we can see, does the yellow galaxy shape tend to be aligned or not aligned with how, depending on how far away it is from the foreground galaxy. And that also, so these all carry information about how clumpy the matter is doing the gravitational lensing. They all have slightly different uncertainties. So what we do is we collect measurements of these three types of relationships on the sky and analyze them all together so that, you know, the relative uncertainties can kind of cancel out to some extent and give us more information about the distribution of matter. And so we have done this, and these observations allow us to make a map of the dark matter density looking out in the universe on the sky. And so this figure is showing the sort of purple shape down here is showing the reconstructed map of matter density that we've been able to make with the dark energy survey. So here, I think the bright spots mean more matter and the dark spots mean less. And that's superimposed on this image of the sky with the Milky Way projected onto it. So this is a map of like the sphere of the sky flattened onto a page in the same way that you would flatten like a globe onto a page for like a world map. And so you can see we've got this kind of funny shape to the survey, but basically it's a big circle part trying to look out the bottom of the Milky Way, because if you're trying to look at faint distant galaxies, you can't see them through our galaxy. Our galaxy gets in the way. And then there's some rectangles stuck on to increase overlap with some other measurements that we can look at together to do some interesting science. All right. So yeah, one of the big products here is making a map of matter in the universe. We can also compare our model predictions to our measurements of all of these different summary statistics. And because we can vary input parameters into our model, like the size of these different pie chart components, we can search a parameter space or basically look at different ways we can approach our model and constrain the possibilities for what the universe looks like. And we end up with results that we plot like this, which what I am showing here are two parameters in the model. On the vertical axis is one describing the amplitude of density fluctuation. So clumpier universe at the top, more uniform universe at the bottom. On the horizontal axis, I'm showing matter density, which is basically how big is the matter piece of the pie chart. And the gray contours, which might be a little hard to see here, show the constraints from our dark energy survey. And what these contours are showing is based on our model comparison to our data, we have the DES, galaxy clustering and weak lensing data. We are about 70% certain that the real numbers live inside this the inner contour, and about 95% certain the parameters are in this outer contour. And so this is how we end up reporting constraints on like the physics of our model. And you know, that's interesting to do in its own right. It's also particularly interesting to be able to compare to similar constraints from different kinds of observables. And one that we're really interested in looking at is constraints that you would get by using measurements of the properties of the very early universe. So I haven't talked a ton about this, but there is light that we can observe that was emitted when the universe was only about 300,000 years old. So basically when the universe first cooled enough that like atoms could form stably. And there's a bunch of light that was released then. And there are temperature variations in that light when we look at it coming from different parts of the sky. And the patterns, and that's visualized in this picture here of like red and blue blobs representing temperature variations. The statistical properties of those blobs can tell you what density fluctuations looked like at early times. So we can make these measurements of density fluctuations at early times, and then given our model, say, I'm going to assume general relativity, cosmological constants, some other assumptions, you can project forward what you expect to see for large-scale structure in the late times. And so the comparison between these two contours is like a test of our model's ability to describe the whole 14 billion year history of the universe. So the red contour is showing what we expect from early universe plus our model. And the gray contour is like a little bit more of a direct measurement of the amount of structure in the universe now. So the fact that these contours are even in the same region of this plot is telling us that our model works pretty well. And then, you know, we might look at, they're a little bit offset. So the fact that the gray contour is a little lower than the red one is telling us that we see slightly less structure in the universe. The universe is a little less clumpy than we'd expect given these early universe measurements. And you know, these overlap pretty well. This particular measurement, it's not really that statistically significant of an offset. But a pretty exciting thing and tantalizing thing in cosmology right now is there are a lot of other galaxy surveys, a lot of other approaches to measuring large scale structure that are seeing a similar offset. And the more independent experiments find this, none of them are that significant on their own yet. But it is, I'm becoming more and more convinced that this is maybe not just a statistical fluke, and there might be some, like, this might be hints at, you know, the simplest model might not quite be matching observation, which is like, as a cosmologist, this is what you dream of, because it's really a triumph that the simplest model, this cosmological constant description, does such a good job at describing so many observables that we have. But because we don't think it's the full story, like, it'd be nice if it didn't do quite as good of a job. And so this might be, and the Hubble tension that somebody mentioned earlier of the measurements of the expansion rate, see sort of a similar offset that has people kind of excited and curious. And yeah, so this is a little cartoon sort of framing this in terms of like why we're excited about this. And so the analogy here is, you know, if we're trying to observe some animal by taking pictures of different parts of it, and maybe you've started out and you have a picture of its nose, it's this bill shape, and you maybe have a picture of a foot and you see this web shape. And so our working model is we're looking at a duck, web feet, billed nose. That's great. And we want to go and make different measurements or maybe sharper pictures or, you know, improve our photography of this animal. And if you gather new data and you think you're going to see a duck tail and you see a tail that looks like it comes from a beaver, you know, it's possible that maybe you're pointing the camera in the wrong spot and, you know, you got some error that you need to correct for. But it could mean that you need to change your model. And so this is sort of an analogy for why we're excited when we make different constraints on the simplest model with different observables, that we get excited because mismatches might be a hint that, you know, we need to start looking for platypuses. So, you know, when we see this kind of mismatch, there's a lot of work to do. We want to work towards making more precise measurements. So using the whole data set from dark energy survey or using these new telescopes or different kinds of measurements to sort of see like, all right, we're slightly offset. If our constraints get better, do they stay centered where they are? Do they jump around? And to see if that offset stays put as our measurements get better. We also want to make sure that, you know, all of the assumptions we're making in our model prediction to do this comparison between models and data, that we make sure we really understand that well, because we don't want to make some mistake and trick ourselves into thinking we discovered what dark energy is, when really we've like not accounted for some messy galaxy astrophysics in the correct way, which is, you know, what I and many of my colleagues spend a lot of time thinking about. And then you can also start exploring models that go beyond the simplest description and see if the data favors adding, like changing the properties of dark energy, for example. And this is what I've spent most of my time on in the past couple of years. This is a very busy slide, but just to highlight a little bit of more specific of what I work on. So I and another postdoc named Anya Sverte, who's been at, I misspelled NASA on this slide, but NASA JPL and now at Stanford, we co-led a team building on the work of the other like several hundred experimenters we work on, but this is just to highlight some of the people that worked on this project specifically. It's a lot of students, postdocs, junior as well as senior scientists. And we use that first 3 years of DES data to constrain several different models which add physics beyond the simplest cosmological constant description of dark energy. So we checked for some time evolution of dark energy properties. We checked for some simple possibilities for how general relativity might be extended. We looked into whether, you know, maybe instead of one type of particle, dark matter could be mostly one type of particle and then another subspecies of lighter particle, which is something that particle physicists might be have some interest in. And so we tested all these models. It was a big effort. I felt like a star because we got a press release from NASA when our paper got posted. So we have a preprint of the paper out. It should be published in a journal any day now. I proved the proofs like a month ago. So this has just been a very exciting thing to get out into the world, and it's been really a privilege to work with all these people. And as we said at the beginning, like, ask the universe what it can tell us. So far, with the current data, none of these extended models we looked at are preferred over the simplest one. So yeah, so far. But there is, you know, exciting science to come. We have we've only analyzed half of the data from the dark energy survey. And, there are these new experiments turning on in the near future. This is a slide where I'm being cute by being both literal and metaphorical to say that, there's even more science on the horizon. What the image is, this is a view from the observing site where the Blanco telescope is, where the dark energy survey is, looking over to the next mountain where it's really not showing up on the slide, but there is another observatory being constructed over there in this picture. And that's the construction site for the Vera Rubin Observatory, which is the next successor. This picture is from 2019. No, yeah, from 2019. So now the Vera Rubin Observatory is almost completed construction. My collaborator recently got to go visit it. And it's the LSST survey, or the Vera Rubin Observatory, is going to start collecting data just within the next year. It's going to collect data over the course of 10 years, and is going to measure 30 times more galaxies than dark energy survey. And roughly speaking, you can kind of think of number of galaxies is statistical constraining power. And so there's a potential for getting tighter and tighter constraints. And as a theorist, it's a challenge and an exciting possibility, because for us to be able to benefit from all of that information in this really exciting data set, we really have to make sure we know where our model predictions are trustworthy, and that, we're checking for all the places where we can accidentally introduce biases into our results. So I guess, yeah, I'll wrap up there since I've talked for quite a while. Yeah, exciting things come.
Okay, let's take a 10-minute break. Leslie, do you have a raffle? Okay, so there's a book up here for raffling, so out there. Yeah, let's take 10 minutes, then we will come back and do some questions and answers.
You're lucky. I just turned this off.
Yeah, sure. Boy, very, very interesting. I had a quick question for you. Your term at Perimeter, were you invited to come to Perimeter for a couple of years?
For a postdoc.
Oh, okay. So Katie Mack and others who come there, they're the firm.
So I know she had visited there now, but she's now a professor there, so she's permanent.
Okay, okay.
Yeah, I mean, they advertise jobs and you can apply for
Okay.
jobs.
So do you research and teach?
I just do research. So
Okay.
I have the option, I haven't actually done any teaching, but I've sort of mentored some students on research projects.
Okay.
I think if I really want to teach, there's some avenues for me to do
Yeah.
that.
I was just curious. It's a great resource, and the fact
Yeah,
that people
yeah.
from all over are coming in.
Definitely feels like a special
Hey.
place.
I have a question that I'm not sure I can phrase properly, so perhaps you can help me in my phrase. Yeah, by all means.
Yeah.
Yeah,
And
absolutely.
actually, if you want to
Yeah.
take a break. by all
I'm
means,
alright.
Okay.
or I
Okay.
can let you.
Do we know anything about the distribution of it? I know you deal on these scales. I'm going down to Milky Way,
Uh-huh.
standard galaxy.
Uh-huh.
Do we know anything about the distribution of dark matter in a standard galaxy? I understand it's more or less just a,
Yeah, so yeah, this is the thing, it's an active area of research. So from simulations and some, I think, pen and paper calculations, and I think observations of the group, there's sort of a description you can end up with it. Our understanding is that you can describe the distributed matter roughly in most cases as spherical blob with some radial distribution and density, and there's a particular form of that seems to be pretty universal to come out from collapse or blob of dust. You get deviations from that because galaxies Mercury, satellite galaxies
Sure.
and things.
oh, yeah,
And so there's a big area of interest is substructure.
yes.
Yeah, and so a thing that people look at, and so before I was at Perimeter, I did 3 years as a postdoc at Stanford, and there's a group there that really specialized on these really high resolution simulations of an individual galaxy called the dark matter, and looking at
Yeah,
satellite galaxies,
Okay.
these little galaxies.
you had the bottom of your projection, there were the two Magellanic clouds. Yeah.
And so there's a lot of interest in, well, so one of the big pieces of interest is if dark matter has very small interactions with itself, or has if we know that it mostly doesn't interact, but if there's very, very weak, you end up destroying structure. If dark matter only interacts through gravity, there's never a limit to the smallest clump of dark matter you can get. But if dark matter either has some interaction or like there's perimeter study descriptions of dark matter that are actually made of like very like low mass particles that are actually low net mass that you have to worry about like quantum wavelengths on like astrophysics. And so what happens if you look at these models is there's a limit to the smallest blob you can make. And so people are trying to study, like if you look at smaller and smaller galaxies, can you figure out what the smallest blob of dark matter is? And if you do that,
You set a limit anyway.
that.
Okay.
So there's a lot of interest in that. People also look into, so part of sort of related to studying like satellite galaxies, what's in this thing called stellar streams, which are, I don't know if it's done other things, I've heard about satellite galaxies with lots of the streams of stars that are kind of orbiting the galaxy.
Yep.
And people do research where they look at the streams, sort of see a little like kink in it or like a missing gap, and they can model like, was this disrupted by maybe a block of dark matter? Like the models are pretty uncertain.
Yeah.
But this is the thing that people are. So.
Question, thinking about your portion of dark energy. Do we think that dark energy was present at the moment of the Big Bang or shortly after? And was it the density of dark matter consistent over time, or did it fluctuate during time?
It would have just always been there. But because, like, if that's the kind of energy density and it's only time anything else is much denser,
Yeah.
smaller, it basically has to. And like the fact that we see accelerating expansion just is like, that's around the time when like matter, dark energy sort of predominates. Yeah.
So that, over time, we expect that that'll continue to be the case, and therefore the expansion will increase.
Yeah. Yeah, it'll approach like
Thank you. Excellent.
Yeah.
like, you know,
Yeah.
Like, energy, it's like very automatic. Like, you can find an electron, the proton, and a proton.
Yeah.
And people consider like different models for dark matter. And so like, there are models of dark matter that might like. But there could be dark matter, anti-dark matter. Yeah, it's not, like, people do study and constrain models, you can say, like, one of the things people look at to try and explain is like amplitude and density fluctuation. If people do look at things of like, what is that model where some small fraction of dark matter is the case, versus kind of radiation. Maybe not like,
Yeah.
but like some like, people talk about like dark spectrum, but you know, it doesn't very matter when you have protons. So. Possibility, that's really like, either favorite things, but also.
Which side do you want?
Yeah.
Dark matter can and because there's some
I'll take the one with the 6.
how much decays.
Yeah.
You have enough like 3 parameters you add to your model. So that ruled out that we're kind of in a state where there are things that are ruled out, things that are not. Like, when you're kind of assessing like, is this model favored over the plus one, you kind of penalize that. And so it's like, it doesn't fit the data better enough to make it worth adding over.
Yeah.
Yeah.
We're really. Like. I mean, like this. We just got those data.
Yeah, and so partially people are excited about the because like. When you're in the standard cosmological law, you can make predictions for how fast matter should pump up and like how hard it is to form galaxies.
Yeah, I think
Galaxy formation is very messy, so it's hard to prediction. But like, the fact that people are seeing these form the galaxies at times, some people said it could be, right, maybe we need this pumping faster earlier. Most, my understanding is that most like dark matter fields, blobs of dark matter, galaxy coming, they have a certain distribution in density, like how the changes from the center to the outer part. And that's universal, but there's like three firms that add a little bit of difference and like. I don't know the direction, but like I think older galaxies tend to be a little bit more concentrated than younger galaxies. I think that's because there's been more time for like gravitational interactions to kill it. So like for them to settle. But this will be different with galaxies that are in dense regions of like other galaxies. But it's an active area.
Hi, I'm Peter Langdon. I just wanted to say how much I enjoyed the summer collection. Feel free to get sent out. A couple of months ago, when I went to this talk, they call it your talk. Interesting. Yeah. So to my little question, and where much of your talking
Yeah, I think that is correct as far as I understand it. So I mean, I feel kind of like the Big Bang kind of statement that the universe was much denser and hotter in early times. The presence of darkness. Thinking that much in the which when so when you go back to like before 100,000 years after the Big Bang, you get things happening where all of your atoms are and you basically go to early enough time to like hotter, like all the matter hotter, everything hotter. And so you like this will act very differently than we're familiar with. So basically, we have the equal dimension square related with energy and so when you get to early times and particles of normal velocity are big enough that it's comparable, you can get particles getting released and annihilated. So if you go back to like early fraction of time, like all different kinds of ordinary matter particles that are only produced now are like popping in and out of existence. And so we some of them like how much matter has to do with how predictable how much hydrogen and helium there today because of the so like the fact we see evidence of like a hot universe expanding and like let us place limits on like if they can come up with some like other description of that kind of debate and stuff. Like people get excited about it. I'm not familiar with like, that's whether that might imply something. But the presence of dark matter. I'm in like a 3-year research position. Yeah, in my field, usually you finish your PhD and you do a couple of these like temporary research jobs, so like collaborative. And try to really, which I'm in the process of
Takes
applying.
time, right? Yeah. I do, I just, I have to really. I don't know. Damien told me. He would be in outreach. Yeah. Yeah,
Spend most of my time. So.
yeah, for sure. Did you actually go to perimeter or do you?
I was like the way like space.
Okay.
Like all of my work is really just kind of computer.
Yeah.
Yeah. So it's, I mean, when I arrived last, like fall 2021, there was a line for but it's live with that. There's the black orchestra. A lot of our seminars. Yeah. So it's motivating. It's a nice building. Yeah.
I've been there, right? Anyway, he did
on the bond?
The weird staircase.
Yeah.
Well, it says 20
Like, yeah, but there's like trying to do the hallway of one thing. So there were stickers on all the stairs for like only go up there. So like I didn't know that only like spending like all my time trying to figure out how to get to my. Silver and mask. It is nice. It feels.
Yeah. They still think to them.
I've not seen that. I'm gonna find the coffee for you.
Oh, nice. Oh, I don't know. Science writer. So I do education, I mean, education. So I've done the third program. Oh, people.
This month.
I've done like a for 2 years here. They do. I worked on a lot of different applications for them. I haven't, but I used to. There's some fun. Yeah.
Yeah. Well, how are you saying that's like, you know, some community building within.
Yeah. Yeah.
And then there's like. Where the Maryland University.
Oh, yeah.
Like getting that underground. I would have to do all of the like. It's like so nice to work with. I mean, like, it's special.
It is, it really is. Yeah, yeah, I love going there. I enjoyed it. Yeah.
Together in this particular way. Yeah.
I think everybody, you know, what's to the left, right? Yeah. I love all the cartoons. Awesome.
It's like, some of them are, I just got an iPad and was trying to look at it. Some of them are really a note taking app, and then some of the more like polished ones, like the
plastic one was pretty
yeah,
polished.
yeah, that's what I actually learned. So that was one of my pandemic hobbies was like, so for, yes, we put out a cosmology report. There's actually like a match of like 30 papers with all of what like different and that's like, there's not like an official, there's not like a budget. Within the collaboration. There are people interested in it. There's something like, all right, you know, there's 30 papers coming out, concepts are waiting. And so we decided we were gonna do like. Or maybe not. Daily scrolls. And so like, I think I ended up doing like 7. Like, sort of took different papers to try to. It was a lot of fun. We ended up doing it. So a lot, like the planet was for human. And then like. Yeah, that is run out of. So it's kind of a nice.
The stock market would be this-
Yeah, I mean, there's yeah, but I was saying, like, the thing that I like.
That's one of the big-
Like, I do things like. I mean, I assume they. Or like, you know, if you just.
No, it's,
Be an idea now. I just want to know. You're right. Do you just say-
all right, let's start up. Testing, testing.
We hear you, Randy.
Can you hear us?
We got
Yes.
Okie dokie.
Yeah. Yeah.
Can you see us?
Yes, I can see you.
Okay. Let's go through questions. You've asked, how many questions? I'm gonna go through the. Yeah, if you could just, that'd be great. I have them.
Am I
here.
reconnected? Okay.
All right. Someone asked, they saw some satellite dishes on the side of the big telescope. I think they might have been microwave or something or other. They weren't necessarily astronomical. Data. Yeah, probably. Yeah, those things on the side there. Yeah, probably just.
Yeah, I'm not really sure. There's also like a lot of like weather monitoring stuff. So like on the mountaintop that you can't see in this, there's a bunch of other domes. There's little smaller telescopes. There's also, I'm blanking on what it's called. There's a little one that monitors like cloud cover. It's like when you try to observe on nights where there's not clouds, but like you kind of track how many there are to keep track of like the quality of the observations you're making on a given
So if
night.
you get haze, that's going to affect your data.
Yeah,
right?
it's harder to see galaxies through haze,
Yeah.
or it's also harder to see galaxies on like nights when the full moon is out. And so they particularly like will choose which colors to observe because some of the filters are more or less sensitive,
Oh, okay.
and they track all of that information. So a thing that I kind of glossed over is like, we're measuring these statistics of galaxy clustering. We want to make sure that when we're measuring an overdensity of like galaxies on the sky, it's actually a physical overdensity of galaxies on the sky and not, well, we had a new moon on this night and a full moon on this night. And so there's this whole process that there's actually like, I was telling somebody during the break that when we put our cosmology results out, there's a batch of like 30 scientific papers that all come out with it about different aspects. And one of them is on this process of like having all these templates of like, this was the sky brightness and this was the observing quality, and trying to account for that when you're making these statistical measurements to make sure you're not mistaking observational circumstances
Sure.
for physical density fluctuation.
Okay, is the resolution high enough to spot supernovae?
Yeah, so a thing that I glossed over, and I don't have the map that I'm thinking of in this talk, but there's a whole, so in the same way that like, I'm talking about the large scale structure science for DES, there's efforts within the collaboration to look for solar system objects, there's all these different kinds of science. And one of the like big areas of focus of the survey is that within the big galaxy survey, there's another supernova survey. And so of this big 5,000 square degree patch of the sky, there's some smaller patches that are revisited with this telescope at an even more like frequent cadence. So So the unique thing about supernova is that they change over time. And so to try and find things that are changing, you want to image the same patch of the sky many, many times. And so I don't remember offhand how many they've found, but there's specifically an arm of DES that has these patches of the sky that they make these really frequent observations of to measure supernova. And to do these kind of like Hubble diagram measurements of expansion history. It's a little bit more, you have to gather a little bit more data to be able to do that, because we're this imaging survey, we can see the supernova. But like to get this precise like distance information, or like to calibrate their brightness, or what we think the actual brightness is, you need precise color information. You need to make sure that supernova you're observing is the specific type that we can use as a standard candle. So right now what the status is we use the imaging surveys like supernova survey to find supernova, and then people with telescopes that can go and measure spectra, follow them up and measure the spectra. And this is sort of the volume of the survey is sort of pushing the envelope of what we can do with that. And when like LSST, the Vera Rubin Observatory, turns on, you know, if they're imaging the whole sky every couple of nights, they're going to find a lot of supernova, and they're going to find more supernova than you can actually follow up with measuring spectra. And so there's an active area of research where people are trying to see, all right, given this small subset that we can follow up with spectra, can we like train AI sort of machine learning things to be able to classify supernova just based on these colors? And so that's sort of an area, because like you're going to have a huge sample of supernova, which means you could learn a lot about expansion history, but only if you can classify them.
What's the total size of your data?
What's the total size of the
like-
data set?
In terms of like,
Petabytes?
Floppy disks.
yeah, I do not know offhand.
Okay.
A lot.
Yeah,
Yeah.
I know there's a couple 100 million objects. And for each object, you have color measurements, state measurements. So I don't know. The data is all public. Well, at least the first 3 years of data is all public online. So if you want to go online and look at it, yeah. But it's quite a lot of data. Yeah. I mostly work with it in this like summary statistic format, which in practice means I'm working with like 500 numbers, which is a very condensed version of the data set.
It's in the cloud, but it's the size of the Magellanic Cloud. That's a little humor there. Do you use any machine learning in your research to
Yeah.
handle the data?
So at different points in the analysis, machine learning is used. So a big, well, I would say like personally, the aspects that I would use that are, there are types of doing statistics on a computer that when you ask some people, is this machine learning or not, different people will answer in different ways. So I do a lot of like quote unquote big data statistics on a computer, and to like get this type of result. So going from the summary statistics, these measurements, we're searching a parameter space for our model, and I'm showing 2 of the parameters on the slide, but our model actually has like 30 parameters in it. And so you can kind of think of why, so we can think through why this is a challenge. If you have one parameter you're varying and you want to say which value of this parameter is the best fit, you can like measure 100 or try 100 different values of that parameter, compare it to your data and say this one fits the best. If you have 2 parameters and you want to measure 100 values of each one, you're ending up with 10 to the 4th power of these measurements. 30 parameters, your computer is not going to be able to do that if you just make a grid. So we have to use specific algorithms for searching this parameter space to figure out where to put these contours and to make sure we're capturing our uncertainties right. So this, I think I took a machine learning class in grad school, and this counted as machine learning then, which I was surprised by because I was already doing it. And, but there are other parts of the analysis where like things that fewer people would disagree are machine learning are used. So one of the big things is that, what we have in terms of galaxy color measurements is we have the galaxy brightnesses in 5 color filters. And we want to map that onto an estimate for the distance of the galaxy, or the redshift of the spectra. We don't have the actual spectra of the galaxies. And so if all galaxies have the same spectrum, you can look for certain features in the brightness and say, as this feature passes from one of these wavelength ranges to another, we'll see the relative brightness change. And so you can, if you measure spectra from a subset of galaxies, you can train an algorithm to say, all right, this collection of 5 brightness numbers corresponds to this distance. Challenges come up in that all galaxies are not the same. Some of them have different features. And so there's this mix of like galaxy properties and distance that influence these brightnesses. And a challenge is to be able to measure spectra, usually working with brighter galaxies, and with these images and things we're measuring shapes are, they tend to be very far away. So it's hard to be sure we have like a representative sample that we're training our machine learning with. And so this is another, maybe 1 or 2 of those papers in the 30 paper set of like trying to train a machine learning algorithm to estimate distances based on colors, and then also try to quantify, which often ends up being the hard part, how certain or uncertain are we, and like is how we calibrate that affecting our results. So that's one example.
We realized at our annual meeting last month that at 10 o'clock, everything shuts down.
Oh.
So I'm going to take one more question from the chat and then maybe one more question from the audience. So if we could keep it to a quick Q&A.
Yes or no?
That's unfair. How did cosmologists determine that 70% of stuff in the universe is dark energy and 25% is dark matter?
Yeah, so we have a couple different approaches, but roughly speaking, we have our cosmological model, these assumptions that go into it. Given that our description of gravity is general relativity, we can make predictions for how we expect the expansion to change over time, how we expect structure to plump up over time. And we compare, so we have those pieces of the pie chart are like dials we can dial in our model. And for these collection of measurements, we see which sort of input values, 70% versus 75% versus 40%, which fits better or worse to the observation. So roughly speaking, different kinds of observations all tend to agree on this roughly 70-25-5 split. Details vary, but.
All right, one more question from the audience. Chris?
Are the Starlink constellation satellites going to affect your data the many others that are?
Yeah, so I forget the exact number, but but I know some of the scientists in like the Rubin analysis here look, because basically all the images I showed you of data from DES are cleaned up. But if you're looking at the raw images, if a satellite goes through, it's a big streak. You have to cut those pixels out. You have to cut pixels out around it because it'll like bleed a little bit in the detector. And so I think somebody did an estimate of like the Rubin LSST is going to observe for 10 years. And the effect of like Starlink and all the data you have to chop out is going to decrease the effective science it can do by a couple of years. So like all of this investment is just, yeah. So I know there's some active discussion. I'm not really sure of the status of it, but yeah, it definitely will interfere with ground-based astronomy, this kind of survey science.
I think we have time for one more.
Ask him.
Oh, yes. Okay, yes.
Wow, that was painful.
Quickly, Kate.
It's okay. Come on. Earlier in the year, there came up with observations that do not understand that dark energy is somehow a product of supermassive black holes. Is that something you need to take into account when you do your research, or is that just something other people are talking about?
And maybe repeat if you can.
Yeah, so the question was about this result that came out, I guess like a month or two ago, that suggested that maybe dark energy could be some property of black holes, and there were some observations that seemed to support that idea. So I am not an expert in like the details of the difficult general relativity of really describing black holes. I think it's something that caught interest. I think from what I understand of the result, I don't find it particularly like compelling, but if more observations support it, it definitely is something that would be interesting. I don't quite understand how it would work, but yeah, it would be exciting if it holds up. Definitely a thing to keep an eye on. But as a cosmologist, but who's not an expert in like the black hole details. It's, I don't know. I'm interested, but not like super compelled, I guess. But yeah, anything that could explain dark energy is like interesting to me. So, you know.
So we have an offer from a viewer here. Can we contact you in about a year if we have an idea for a capstone project for an AI certificate, IEI, an idea that can help you in your work? I'll do it for free, of course. You can say
I'm
that.
not, yeah, I'm not sure what all of these things are. I think there's, I mean,
People are interested. That's the
yeah,
main-
and I don't know if this is a student or somewhere else, but there is a lot of interest in like machine learning and cosmology, and there are various workshops and things around, especially for students or undergrad students. I know like University of Montreal is hosting like a summer school thing that people can
Mhm.
apply towards. And there's a lot of ways to ramp
Yeah,
up and learn
great.
about this.
I think that's a great place to stop. Thank you very much, Dr. Muir. Yeah, appreciate it very much.
Thank you all for your great questions.
Before we get shut down, I'll ask Leslie to come up and we can check the raffle. And if we lose the Zoom people for our next meeting, check the website. It's sometime in,
I just stopped sharing.
okay. Oh, no, yeah, you can just stop that. Yeah, that's.